we're going to do some practice problems with different gas laws. So let's start with this one. A bicycle pump has a volume of 1,400 cubic centimeters. And as you read this, I'm going to write down what we know. So I'm given a volume, and we're going to call it VI or V1, initial volume of 1,400 cm3. If a sample of air in the pump has a pressure of 730 millimeters of mercury, so we're going to say, well, with that volume, we also have a pressure, or initial pressure, or P1, of 730 millimeters of mercury. What is the pressure? So we want to know P2. We're going to call this P1, V1. We want to know P2, question mark, when the volume is reduced to 460 cubic centimeters. So we've got V1, P1, V2, we want to know P2. So hopefully you're able to recognize that this is a Boyle's law problem because we're dealing with changes in pressure and or volume of a given amount of gas that's at a constant temperature. So we know that Boyle's law is P1 V1 equals P2 V2. And we need to solve for P2. So in order to do that, I have to divide both sides by V2. To find the pressure, we need to do P1 times V1 divided by V2. Now we just need to plug in what we know. So our P2 is equal to 730 millimeters of mercury times 1,400 cubic centimeters, all divided by V2, divided by 460 cubic centimeters. That will cancel, leaving me with millimeters of mercury. So let's just plug it in. 730 times 1,400 divided by 460. And we should get, let's see, we want how many sig figs? 2 sig figs for all of this. So P2, I just want 2 sig figs. So we'll make that 2.2 times 10 to the third millimeters of mercury. Or you could always write it, if we only wanted 2 sig figs, 2200. Which, if we think about this, my volume decreased from 1,400 to 460. So, and my pressure went from 730 up to 2,200. And that makes sense because we know Boyle's law is an inverse relationship. If volume decreases, then pressure must increase. And it did. It increased from 730 up to 2,200. Let's look at another sample problem. Here we have a large balloon that contains 65 liters of helium gas at 25 degrees and a pressure of 745 millimeters of mercury. So we're given volume, 65 liters. We're given temperature, 25 degrees Celsius, I guess it's not 25, and a pressure of 745 millimeters of mercury. Okay, the balloon ascends to 3,000 meters, at which the external pressure has decreased by 30%. So to do this, if it's decreased by 30%, I'm going to find out what 30% of 745 is, and then do 745 minus that. So 745 times 0.3 is 223.5. So we're just going to do 745 minus 223.5 because that's 30%. So 745 minus that 30% should be 521.5. And we're in millimeters of mercury. And just to make sure that that makes sense, we could also do if I did 70% times 745, it should give me that 721.5, right? I found 30% of 745, and then I subtracted that from my answer. So good, we're good. 521.5 millimeters of mercury. So my pressure decreased. What would be the volume of the balloon? So volume 2 is a question mark. Assuming that it expands so that the internal external pressures are equal. Assume the temperature is still 25. Okay, so temperature is staying constant. So I'm going to just ignore the fact that I wrote T1. So we're given volume 1, I need to find volume 2, and pressure is decreasing. So this is another Boyle's law problem. So we just need to solve for volume 2. We know P1 V1 equals P2 V2. To solve for volume 2, we just need to divide both sides by P2. So let's do that. P1 V1, so 745 times 65.0 liters divided by P2, 521.5. Now we just need to do 745 times 65 divided by 521.5. And our volume should be in liters because millimeters of mercury cancels out. And how many significant figures do we want? Three. Looks like 3 significant figures. So 92.9 liters. And let's see if that makes sense. My pressure decreased. So if one is going down, the other must go up. 65 liters is what I started with, and it went up to 92.9 liters. All right, good job. Here's a question that says that we have a sample of a gas that has a volume of 25 milliliters. So we're given a volume of 25.0 milliliters at room temperature. So T1 is 20.0 degrees Celsius. What is the final volume? So we want to know V2 question mark. If you hold the syringe in your hand and raise the temperature, so T2 is raised to 37 degrees. We hold the pressure constant, so pressure is not changing. So here we're given an initial volume, it wants the final volume. We're given an initial temp and a final temp. So hopefully you could recognize that, oh, this has got to be a Charles's law problem. Charles' law says that V1 over T1 equals V2 over T2. Charles' law says there's a change in volume of a gas sample with temperature change. So we want to know volume 2. I always like to make fraction problems linear. So I'm going to say that these two times each other, so T1 V2 equals V1 times T2. I like to set mine up like that. Then if I go, okay, well, how do I get just V2 by itself? Well, then we got to get rid of T1. So we'll divide both sides by T1. Now we can say that V2 is equal to V1, so 25.0 milliliters, times T2, 37 degrees Celsius, divided by T1, 20 degrees Celsius. But also keep in mind, we have to have our degrees Celsius temperatures in kelvins. So I'm going to add 273 to both of these because we know that Celsius temperatures can go into negative numbers, and that's not going to work for our problems here. So I'm going to do 37 plus 273. So this is actually going to be 310 Kelvin, and 20 plus 273, this is actually going to be 293 Kelvin. Now we can plug it into our calculator. So 25 times 310 divided by 293. And we should get 26.5 milliliters. Volume 2, 26.5 mLs. Let's see if that makes sense. Our temperature increased and our volume went from 25 to 26. Volume increased. That's good. Yes, they are directly related to one another. All right, here we've got a balloon inflated with helium to a volume of 45 liters. V1 is 45 liters at room temperature, so T1 is 25 degrees Celsius. Before we even get going further, I'm just going to change my Celsius to Kelvin right now. So I'm going to do 25 plus 273, so it's 298 Kelvin. It's 298 Kelvin. So V1, T1. If the balloon is cooled to, okay, so it's telling me that its temperature is changing, T2, to negative 10 degrees Celsius. All right, let's figure out what negative 10 plus 273, so 263 Kelvin. What is the new volume? V2 question mark. So we can see that this is also a Charles law. Assume that pressure does not change. So V1 over T1 equals V2 over T2. I'm going to write it linearly. So I can say that T1 V2 equals T2 V1. I want to solve for V2, which is right here. So divide by T1. V2 is equal to T2, so 263 Kelvin, times V1, 45 liters, divided by T1, 298 Kelvin. 263 times 45 divided by 298. We should get 39.7. And our volume is in liters. Again, let's make sure that it makes sense. My volume went from 45 to 39, so volume went down. Temperature went from 298 to 263. Temperature went down. Yes, they are directly correlated with one another. There's one. We have helium-filled balloons are used to carry scientific instruments high into the atmosphere. Suppose a balloon is launched when the temperature is, before I get any further, I'm going to write 22.5 degrees Celsius, which is, let's go right to Kelvin, 22.5 plus 273, 295.5 Kelvin. Okay, we've got T1. The barometric pressure is 754, so we're going to say P1, 754 millimeters of mercury. It's important to write down your units. Remember, we've looked at pressure in atmospheres and kilopascals and pascals and bar, and they all have different conversion units, so we've got to write down what we're dealing with. If the balloon's volume is, so we know volume, 4.19 times 10 to the third liters, and no helium escapes from the balloon, what will the volume be? Okay, so we just said, what is the volume? What's it going to be? Question mark. At a height of 20 miles, where the pressure is, okay, pressure 2 is 76.0 millimeters of mercury, and the temperature is T2, negative 33.0 degrees Celsius, which I'm going to say negative 33 plus 273, 240 Kelvin. Okay, so in this case, we've got temperature decreasing. We've got pressure decreasing. We want to know what's going to happen to the volume. This looks like we're using the general gas law, where it's P1 V1 over T1 equals P2 V2 over T2. This is our combined gas law, and we want to find V2. So again, I don't love the fractions. It can be confusing to some. So I'm just going to combine diagonally again, just like what we did this last time, the last couple that we've done with Charles's law. So I'm going to say P1 V1 times T2 equals P2 V2 times T1. And now I just want to solve for V2. I want this guy out by itself. So I'm going to divide by P2 times T1, right? I just need to get rid of the P2 and T1. P2, T1. I'm just going to rewrite this so it's a little bit nicer and neater. V2 is equal to P1, V1, T2 over P2, T1. It's a lot of letters and a lot of numbers, so make sure that you are understanding where those came from. All right, now we just got to plug it in. 754. That's our P1. Our V1, 4.19 times 10 to the third liters. P1, V1, T2, 240 Kelvin, all over P2, which is 76, times T1, 295.5 Kelvin. Plug in our 754 times 4.19 times 10 to the third times 240, and then divide that by 76 times 295.5. And we should get, let's see, three significant figures. Looks like 3.38 times 10 to the 1, 2, 3, 4. And our volume would be, those would cancel, kelvins cancel in liters. If we wanted to write this out in long form, we would say 33,800 liters. Why don't you try to set this one up? If we have a 22-liter cylinder of helium at a pressure of 150 atmospheres and at 31 degrees Celsius, how many balloons can you fill, each with a volume of 5 liters, on a day when the atmospheric pressure is 755 millimeters of mercury and the temperature is 22? How would you go about setting that up? So pause the video here and see what you can find. Hopefully, you wrote down your initial pressure of 150 atmospheres, 22 liters was our initial volume, and our temperature of 31 degrees Celsius is 304 Kelvin. We want to know how many balloons can we fill. So we want to know our total volume first. So we need to find V2. We're told the atmospheric pressure is 755 millimeters of mercury, and hopefully you went, oh, wait a second, those units don't match. So I went from 755 millimeters of mercury to atmospheres. So we have the same units, which is 0.9934. And then 22 degrees Celsius is 295 Kelvin. So we can see here we need to find volume 2. We're going to set it up just like we did this last problem. And then we took that equation P1 V1 over T1 equals P2 V2 over T2. Rearranged that to solve for V2. Plugged in our numbers, and we got 3,223.6 liters. Now let's go back and look and see how many significant figures we would be limited to. We've got 2, 2, 2, 2, 3, 2. I think we're going to finish with 2 sig figs here. So if our volume 2 is 3,200 liters, we're getting close, we're almost done. It wants to know how many balloons can we fill, each with a volume of 5 liters. So I'm just going to take this 3,200 liters and divide it by 5 liters to see how many balloons that would give us. 3,200 divided by 5 should be able to fill 640 balloons. Let's look at another problem here. We've got dinitrogen monoxide, that's commonly known as laughing gas, used in dental procedures as an anesthetic. At elevated temperatures and with the proper catalyst, dinitrogen monoxide can be produced from the reaction of ammonia and oxygen. So here we're given a balanced equation. If you began with 15 liters of NH3 ammonia, what volume of oxygen is required for complete reaction? What is the theoretical yield of N2O, dinitrogen monoxide, in liters under the same conditions? So if we think about this, we know that Avogadro noted the relationship between volume and the amount of gas. So he said that equal volumes of gases under the same conditions of temperature and pressure have equal number of particles. So we're able to relate the volume of a gas at a given temperature and pressure and say that it's directly proportional to the amount of gas. So in this case, because we have a balanced equation, we can say that we have 15 liters of NH3, and we want to figure out how much oxygen is required. So we can simply just look at this ratio, mole to mole ratio. We can say that for every 2 liters of NH3, 2 liters of oxygen are required. So 15 times 2 divided by 2 is going to say that, well, this is going to be 15.0 liters of oxygen required. And let's compare if I had, well, hold on, that's part A. What volume of oxygen is required for complete reaction? So that means all 15 liters of ammonia is going, it also means that I need 15 liters of oxygen required for this to work. So what is the theoretical yield of N2O in liters under the same conditions? So I'm going to start with the same thing that I started with, 15.0 liters of NH3. And now I just want to get to product. So for every 2 liters of NH3, 1 liter of N2O is produced. So 2 liters of NH3 that is available. You don't need to have this written down. But for every 2 moles of NH3 to react, 1 mole of N2O is produced. So 15 times 1 divided by 2 should give me 7.5 liters of N2O produced. There we go, we've got another equation. We've got methane burning in oxygen to produce CO2 and H2O. And it looks like it is balanced. If we're starting with 22.4 liters of CH4, what volume of oxygen is required for complete combustion? How would you go about setting that up? Well, we have 22.4 liters of CH4. Again, we know Avogadro said that the amount or volume of gas is directly proportional to amount of gas in moles. So we can just use our mole ratio and we can say, well, for every 1 mole of CH4, 1 liter of CH4, 2 liters of oxygen is required. So 22.4 times 2 divided by 1 should equal 44.8 liters of oxygen required. What volumes of CO2 and H2O are produced? So if I've got 22.4 liters of CH4, we know that there's a 1-to-1 ratio for CO2. 1 liter of CH4 is required to produce 1 liter of CO2. So that means that 22.4 times 1 divided by 1 would give me 22.4 liters of CO2. Again, we can see that our units are diagonal and crossing out. So that's much CO2 would be produced. And then we'll do the same thing, but we would have a 1:2 ratio of oxygen, so 22.4 liters of CH4. 1 liter of CH4 for every 2 liters of H2O produced. Again, those will cancel, so 22.4 times 2 divided by 1 would produce 44.8 liters of water. There we go, we got another problem here. The nitrogen gas in an automobile airbag has a volume of 65 liters, exerts a pressure of 829 millimeters of mercury at 25 degrees Celsius. What amount of gas in moles? Remember, moles is denoted as N. Now, this is, hopefully you can recognize, as soon as it says mole, that's using our ideal gas laws equation, which is PV equals nRT. We're given P, V, we need to find N, we're given T, and R is just the gas law's constant. So let's rearrange to solve for N, which means I'm going to divide both sides by RT. So N is equal to PV over RT. Let's plug in what we know. We're given pressure, 829 millimeters of mercury. We're given volume, 65 liters. We're given, we know R. R is 0.0821 liters atmospheres over Kelvin mole. And temperature, we're given at 25 degrees Celsius. And remember, we need to get that to Kelvin. If we weren't sure, we would look at this gas, our constant, and be like, oh, yep, we need to cancel our Kelvin. So I'm going to add 273 to this to get 298 Kelvin. Now, what else do we see that's wrong with this? Our kelvins and kelvins will cancel, good. Liters and liters will cancel, good. We want moles, ooh, our pressure is not in the right units. So let's take our 829 millimeters of mercury and get that into atmospheres. And hopefully you remember that it's 760 millimeters of mercury in 1 atmosphere. So let's do 829 divided by 760 to get 1.09 atmospheres. So I'm just going to cross that out and write 1.09 ATMs. That will cross off my units that's in my gas constant, so I'm left with moles. So we're going to do 1.09 times 65. And we're going to divide that by, and I'm going to put parentheses, 0.0821 times 298. We should get I think we're limited to 2 sig figs, so 2.9 moles of nitrogen gas, so N2. Let's look at another practice problem here. The balloon used by Jackie in the historical balloon flight in 1783 was filled with about 1,300 moles of hydrogen. So this is our N. If the temperature of the gas was 23 degrees Celsius, I'm going to add 273 before we even get going too far. So 296 Kelvin. And the gas pressure was 750 millimeters of mercury. What was the volume of the balloon? So here's our pressure. And remember the problem we ran into with our last? We need this to be in atmospheres. So let's take 750 we know there's 760 millimeters mercury in 1 atmosphere. So let's do 750 divided by 760. 0.9868. Okay, so we know that PV equals nRT. We got another gas law because we are given moles. And we want to find volume. So we're going to, in order to solve for volume, we got to get rid of that pressure. So V is equal to N, which was 1,300 moles, R, which is 0.0821 liters, atmospheres, moles, Kelvin, nRT. Our temperature we said was 296, all divided by pressure, 0.9868 ATMs. Okay, so as soon as we plug in 1,300 times 0.0821 times 296 divided by 0.9868. And how many sig figs are we limited to? Two, looks like 2. So 32000, 32,000 liters, or we could write this in scientific notation, 3.2 times 10 to the 4 liters. Either one of those. Moving on, let's calculate the density of CO2 at standard temperature and pressure. That's STP. So let's think about what we know. If we have the ideal gas law equation, which is PV equals nRT, and because we know the amount, or N, moles, is mass divided by molar mass gets us moles, right? If I said I've got 5 grams of CO2, to get to moles of CO2, I would take its molar mass. Let's say I think it's 44 or whatever, but we would take the molar mass for every 1 mole. So essentially we would do 5 times 1 divided by molar mass. So we're doing mass over molar mass. So I'm just going to plug in right here for N. I'm going to write M for mass over molar mass. I'm going to denote as a capital M. So then we could rewrite this and we could say that PV is equal to little m over big M, that's our N, RT. So we also know that density is mass divided by volume. So we can rearrange the form of the gas law here to give us P times M over RT. Right? Because we know density is mass divided by volume. We just said over here that our N with mole was M little mass over molar mass. So to rearrange this equation, if I divided both sides by RT, divided by RT, times by capital M, so I would have PM over RT. Now we just need to think about what else we know. If we know the pressure at standard pressure is 1 atmosphere. M, the molar mass of CO2, if I added up 2 oxygens and 1 carbon, I should get 44.0 grams per mole for molar mass. R, we know our gas law constant is 0.0821 liters, atmospheres over moles, Kelvin. And temperature, we know standard temperature is 273 Kelvin. So now we just need to plug and chug. 44 times 1, so 44 divided by, I'm going to put in parentheses, 0.0821 times 273. And we should get 1.96. Let's look at what our units are. Atmospheres cancel. Kelvin cancels, moles cancel, and we should be left with grams per liter. All right, let's look at this next one. At 1 atmosphere and 25 degrees Celsius, the density of dry air is 1.18 grams per liter. If the air is heated to 55 degrees Celsius at constant pressure, what is its density? So I changed these temperatures here, and we know that from this equation that density is inversely proportional to temperature. We can see that. And we also know that to write that, we could say that density and temperature of 1 is equal to density and temperature of 2. Remember, Boyle's law was inversely proportional. When one went up, the other went down. So if we know that the density of dry air at 298 Kelvin is 1.18 grams per liter at 298, then to find this density at 328 Kelvin, we should just be able to divide both sides by 328 Kelvin. So let's do 1.18 times 298 and then divided by 328. We should get 1.07 grams per liter. Let's see if that makes sense. 1.18 at 298, temperature went up, so density went down. Makes sense? Here we go. Let's look at this next problem. This one's a little bit more in depth. We're trying to determine by experiment the formula of a gaseous compound you made to replace chlorofluorocarbons in air conditioners. You've determined the empirical formula is, oh, I need to write that in here, CHF2, but to determine the molecular formula, you need to know the molar mass. So we find that we have 0.100 grams sample. So I'm going to just write down what we know here. We know that mass is 0.100 grams. And we have a pressure of 70.5 millimeters of mercury. And before we even get too far, I want to convert that to ATM, because we know that when we use our gas law constant, it's in ATM. So 760. So let's do that. 70.5 divided by 760 should give us 0.09276. I won't round it to the very end. Okay, so we know mass, we know pressure. On a 256 milliliter container, so we know that that's our volume. 256 milliliters is 0.256 liters. And we're at a temperature of 22.3 degrees Celsius. I'm just going to add 273 right away. Plus 273, 295.3 Kelvin. What is the molar mass of the compound and what is its molecular formula? Okay, so we have everything down that we know. Now, we also know that dividing the mass of a gas by its volume gives us density, right? We know that density is mass divided by volume, which is related to the molar mass from the equation that we were using before. Remember when we said PV equals nRT and we plugged in for N, mass over molar mass. So when we rewrote that, here we have PV equals nRT. I substituted for N, molar mass is mass over molar mass, but I want to find molar mass. And so what I'm going to do is I'm going to multiply both sides by M to get rid of M. So I'm going to multiply M to get rid of that. And again, we know that density is mass divided by volume. If I divide both sides by volume, divided by volume, here we have M over V, which is density. So I could rewrite this equation again and say molar mass times pressure is equal to density, mass over volume, times R times T. Okay, so let's solve for question 1 first, which says, what is the molar mass I just want m, so we're going to divide both sides by p. So now I have molar mass is equal to density times R, our gas law constant, times temperature over pressure. Let's solve for that first. So we were given, we need to find density. Thank goodness, we got what we need to find density. Density is mass over volume. There's our mass, there's our volume. So we're going to do 0.100 grams over 0.256 liters. Let's do 0.1 divided by 0.256, 0.3906 grams per liter is my density. So now I'm going to plug it into here. My molar mass is equal to density, so 0.3906 grams per liter times R, 0.0821 liters, atmospheres, moles, Kelvin, times temperature, 295.3 Kelvin, and all divided by pressure, which we found was 0.09276 ATMs. Okay, so molar mass. Let's just make sure that everything's going to cancel out. ATMs, ATMs, liters, liters, Kelvin, Kelvin, and we should be left with grams per mole, which is molar mass units. So now we just need to do 0.3906 times 0.0821 times 295.3, all divided by 0.09276. So 102, the molar mass is 102.0888 grams per mole. All right, that tells me what the whole compound is. But do you remember way back when we found empirical formulas, and we were told that this empirical formula is CHF2. If we knew the empirical formula and we knew what the molar mass of it was, of the molecular formula, we could divide them by each other. So first, let's find our empirical formula's mass. 1 carbon, 1 hydrogen, and 2 fluorines mass should be 51 grams per mole. So let's take our molecular 102 that we just found, divided by 51, and we should get about 2. What do we do with this 2? That means that we need to multiply everything in my empirical formula by 2. So times it by 2 to get C2H2F4. And if I added up 2 carbons, 2 hydrogens, and 4 fluorines, we should get a molar mass for that compound to be 102.0888. All right, let's see what this one's asking us to find. We've got a 0.105 gram sample. That's our mass. The gaseous compound at a pressure in a volume of 125 milliliters and at a temperature of 23 degrees Celsius. What is its molar mass? All right, so we can use that ideal gas law equation, PV equals nRT. Remember, in place of N, moles, I can have mass over molar mass, which is equal to N. So if I have PV equals little m over molar mass times RT, I want to find molar mass. I want to find big M. So let's get it out of fraction. Let's multiply both sides by M, so that'll cancel out that M. And then to get M by itself, I just need to divide both sides by PV. So we would have mass RT divided by PV. M equals mass times R times T, all divided by pressure times volume. All right, so we've got our mass, which is 0.105 grams. R, our ideal gas law constant, 0.0821 liters, atmospheres over moles, Kelvin. Oops, I have to do that. Our temperature. Temperature, we were given 23 Celsius. I need it in Kelvin. So let's add 273. So you get 296 Kelvin divided by. So we need pressure and volume. Pressure is 561 millimeters of mercury. Let's get it into atmospheres. 561, 760 for 1 atmosphere. So let's do 561 divided by 760, 0.7382 atmospheres. And our volume, we need, so that's atmospheres, atmospheres, kelvins, kelvins. I need in liters. We were given milliliters, so let's make 125 milliliters into 0.125 liters. And let's do the math. 0.105 times 0.0821 times 296, all divided by 0.7382 times 0.125, parenthesis, we should get 27.7 grams per mole for the molar mass of this compound. Moving on, we've got a problem here. Hydrogen gas is produced in the reaction of lithium and water. We've got lithium plus water to give lithium hydroxide and hydrogen gas. What mass of lithium is required to produce 23.5 liters of hydrogen gas? Okay, so I have a volume of hydrogen gas. I've got a temperature for my hydrogen gas and a pressure for my hydrogen gas. Okay, so we want to get to mass of lithium. All right, we want to get to mass of lithium. Well, in order to do that, to get to mass, I need to know moles of lithium. I know a mole-to-mole ratio of lithium to hydrogen. Let's figure out how many moles of hydrogen we have that's being produced. If I know that the ideal gas law, PV equals nRT, I can find moles of hydrogen, compare moles to moles of lithium, and then get to grams of lithium. So we just need to work backwards here. We know that our R is liters, atmospheres, moles, Kelvin. So let's get this into atmospheres. So we're going to do 743, 760. So 743 divided by 760 should give me 0.9776. I got 0.9776 atmospheres. So that's our pressure, that's good. Volumes in liters, that's good. Let's get Celsius to Kelvin, so plus 273. So 273 plus 17 should be 290 Kelvin. All right, let's plug it all in. P, so we're going to get N, so we're going to divide both sides by RT. N equals PV divided by RT. Let's plug that in there. Pressure, 0.9776 times volume, 23.5 liters, all over 0.0821. And Kelvin, 290. Let's do the math. 0.9776 times 23.5 divided by 0.0821 times 290. You should get 0.96 6.949 moles of H2. Now, if I look at my mole to mole ratio, 1 mole of H2 produces or requires 2 moles of lithium. So let's do that ratio, 1 mole of H2 for 2 moles of Li. And we know that we want to go from moles of lithium to grams of lithium. So if I looked at my periodic table, there's 6.941 grams of lithium and 1 mole of lithium. Okay, so let's just continue out this equation. I've got 0.9649 times 2 times 6.941, all divided by 1. So I should end up with 13.4 grams of lithium is required to produce this much hydrogen at that temperature, at that pressure. I just simply found out my N, my moles of hydrogen, using PV equals nRT. So I got moles. I went moles to moles using my stoichiometric ratio, and then moles to grams of lithium. Let's look at another problem here. We've got 15 grams of sodium. Reacts with water. Okay, it looks like I need to write a chemical equation here. I've got sodium reacting with water. What volume of hydrogen gas is produced? Okay, well, so we got to think about what my products are. I'm going to have sodium hydroxide plus hydrogen gas. Now I need to balance this reaction here, and I need, let's see, I've got 2 H's there, 2 waters, 2 sodiums. All right, so I have a chemical equation here. Now, I know that I have 15 grams of sodium. What volume of hydrogen gas is produced at 25 degrees Celsius? Well, so first thing I'm going to do is I'm going to make this into Kelvin, plus 273. So I've got 298 Kelvin and a pressure of 1.10 atmospheres. We need to do some stoichiometry here. I'm going to take my 15.0 grams of Na. I'm going to figure out how much hydrogen, as far as moles of hydrogen, is produced. So in order to do that, I need to go from grams to moles of sodium. And if I look at my periodic table, I should see that there's 22.99 grams of Na and 1 mole of Na. And then I can look at my stoichiometric ratio here, and there are 2 moles of Na per 1 mole of hydrogen gas. So grams of Na, moles of Na, moles of Na. So let's figure out how many moles of H2 15 grams of sodium gives me. 15 times 1 times 1, so 15 divided by 22.99 times 2. 0.3262 moles. We won't run until the very end. So now I can plug this into my PV equals nRT for hydrogen. I know that my pressure, well, what do I want here? I want volume. So let's just get V by itself, make it easier. Volume equals nRT over P. So I know moles of hydrogen, 0.3262 moles, are, you know, our gas constant, 0.0821 liters, atmospheres, moles, Kelvin. Temperature we just found was 298 Kelvin, all divided by pressure, 1.10 atms. So let's find the volume of gas here. 0.3262 times 0.0821 times 298, all divided by 1.10 atmospheres. And we should get 7.26 liters. Let's make sure 3 significant figures. We have 3, 3, and 3. So we'll finish with 7.26 liters of hydrogen gas. All right, the next problem up, we've got halothane. Here's its chemical formula. It's a non-flammable, non-explosive, non-irritating gas that was widely used as an inhalation anesthetic. The total pressure of a mixture of 15 grams of halothane vapor and 23.5 grams of oxygen gas is 855 millimeters of mercury. This is my total. What is the partial pressure of each gas? All right, well, the first thing we need to do is calculate our mole fractions. So I've got 15 grams of this halothane vapor. So let's start with our 15 grams of C2HBrClF3. Let's get grams to moles. If I added up 2 carbons, 1 H, 1 Br, 1 chlorine, 3 fluorines, I should get 197.4 grams for 1 mole of halothane. And so this should give us 0.07599 moles. All right, we also know that we've got 23.5 grams of oxygen, of O2, and 16, we've got 32 grams of O2 and 1 mole of O2. So 23.5 divided by 32 should give me 0.7344 moles of oxygen. And this is a halothane. All right, now we also know that the total amount of gas, because I've got a mixture of 15 grams of this and 23 grams of this, the total amount of gas is both of mine combined together. So my total amount here would be my moles of halothane, 0.7599 moles of halothane plus 0.7344 moles of oxygen. Let's add these two together. 0.7599 plus 0.7344. So I have a total of 0.81039 mole total. Now we can do part divided by whole. I know my whole and I know each part. All right, so let's figure out these mole fractions. If I looked at halothane, I would do 0.07599. So this is my part, mole, divided by my whole, 0.81039. So my part mole fraction is 0.0938, we'll say is my mole fraction of halothane. Let's look at my mole fraction of oxygen. So that part, 0.7344 divided by whole, 0.81039. .9062. And if we notice, halothanes and oxygen added together equals 1, right? Because 1 would be representative of a whole. So oxygen is 0.9062 and halothane 0.0938. Both of those together equals 1. Now when it comes to finding the partial pressure of each gas, we need to take the mole ratio of the gas times it by the total pressure. So in the halothane, to find the partial pressure of halothane, I need to take halothane's mole ratio, so 0.0938 times, we were told the total pressure was 855 millimeters of mercury. And so we're going to do 0.0938 times 855, and I should get 80.2. So the partial pressure of halothane would be 80.2 millimeters of mercury. Now let's find the partial pressure of oxygen. So we need to find them, take the mole ratio of oxygen, 0.9062, times the total pressure, 855. And this is for oxygen's partial pressure. So 0.9062 times 855, 774. And we want 3 sig figs, 0.8, so this will round up to 775. We're going to wrap up these practice problems with a bunch of problems that are written out multiple choice, and I would recommend you pausing the video to work through them to try to figure out the correct answer. I'll go through these. We're not going to work through all of them. What I would recommend doing is pausing the video, working through it, and then you'll see that I'll move on to the next slide. So in this example, again, I would recommend pausing it, and then hopefully you got this answer, the 463 milliliters. Here's another sample problem. Again, I recommend pausing your video, and hopefully you got 120 degrees Celsius. Hopefully you got the volume is larger. Is it 11 or 5.1? Hopefully you found it to be 5.1. Hopefully you got 4.5 liters. This one is our last one. I'll put on your multiple choice questions here as soon as you write down everything that you're given. Here's your choices. So you might need to pause and back up to see the problem again here in a second. And then hopefully for your answer you got this. All right, that sums up our gas laws chapter. Again, if you need more practice, please see the supplemental instructions and practice problems with answers.